Hello again, welcome to our Lesson 5 lecture. Lesson 5, talking a lot about double integrals, and big thing about Lesson 5 is the Gauss-Green formula, which we'll get to later on today. Let's start here with double integrals. So a double integral over a region R of a function represents the net volume. The double integral of a region R of a function is basically the volume above the xy plane subtracted by the volume below the xy plane. Okay, basically we are moving from two-dimensional integrals that measure area to three-dimensional integrals that measure volume. So we're going to take a look at a couple examples here. When computing double integrals, you always work from the inside out. So for this first example, basically we're going to be doing dy first, and then dx after that. Okay? So when integrating dy, we're integrating sine of x with dy. Sine of x is basically just a constant. Okay? So our first integral here is going to be, we keep the 1 to 5 integral on the outside. We integrate sine x with respect to y. That's just going to be sine x times y. From x to 2x, and then don't forget our dx is still there. Substituting in 2x minus x and then combine the terms, because really what we have here is 2x sine x minus x sine x, so we're left with just x sine x dx, which you might recognize that as an integral that's not possible to do. Okay, but you did learn a way around that in BC last year. Hopefully you recognize this formula. That's right, we're going to do this integral by parts. Okay? So we're going to let u equal x, and we're going to let dv equals sine x dx. So then du is obviously just 1 dx, and v would be negative cosine x. So now we can rewrite our integral as uv, so it would be negative x cosine x minus the integral from 1 to 5 of v du. So minus cosine x, so that would just be plus, then we change that to plus cosine x because the minus out in front, and then du is just dx. Forgot our 1 to 5 here. All right, I'm not going to put the 1 to 5 in yet because I'm going to integrate that second part first. So negative x cosine x, and then the integral of cosine is just sine. So this is all from 1 to 5. Putting 5 in there, we get negative 5 cosine 5 plus sine 5 minus negative 1 cosine 1 plus sine 1. And really that's as good as we can do here. Okay, and there's no like terms to combine. If you want to distribute that negative sign to the second part, maybe make it look a little bit prettier by not putting a negative first, that's fine, but this is unnecessary. If you want to leave it as a step above, that would be fine. All right, the second one. Okay, so we're going to integrate dy first, which means we're going to integrate that expression e to the x plus y with respect to y first. Okay, before I do that though, I'm actually going to rewrite this as e to the x, e to the y. It's going to make this a little bit easier on us, in my opinion. So we're going to integrate that expression with respect to y. So e to the x is basically a constant. You know, think of this as the integral of 2e to the y dy. It's the same thing. Okay, so e to the x is just our constant that remains, and then the integral of e to the y is just e to the y from 0 to 4 dx. Okay, now we can substitute 4 and 0 in for y, and we get this. Which we can simplify and distribute to e to the fourth e to the x. Remember, e to the 0 is just 1, so that'd be minus e to the x dx. And now we can integrate this with respect to x. So we have e to the fourth e to the x minus e to the x. That integral is just basically the exact same expression from 1 to 3. So we have e to the fourth e to the third minus e to the third minus e to the fourth e minus e. Again, technically that would be fine. If you want to make this look a little bit prettier, that'd be great. So e to the seventh minus e to the third minus e to the fifth plus e. Can't do anything else with that. Third one here. Now we're going to integrate with respect to x first, and then y. So integrating first with respect to x, that means y cubed is just a constant. So y cubed stays there, and then it's x cubed over 3. From root y to y dy. Substituting in the y, we get y cubed over 3 minus root y cubed, or in other words, just y to the 3 halves over 3. And let's distribute this to make this a lot easier on ourselves. So y cubed times y cubed is y to the 6th over 3. Y cubed times y to the 3 halves is y to the 9 halves over 3 dy. And now we can integrate this with respect to y. So this would be y to the 7th over 7 over 3, so y to the 7th over 21. Okay, and then this would be y to the 11 halves over 11 halves, which is the same thing as multiplying by 2 elevenths. So 2y to the 11 halves over 11 times 3, 33, from 1 to 4. Substituting 4 in there, we have 4 to the 7th over 21 minus 2 times the square root of 4 to the 11th. So we can just write that as 2 times 4 to the 11 halves. That's fine too. Or 33. And then put 1 in there, so 1/21, 1 over 21 minus 2 over 33. And that's an absolutely fine answer for us right now. If we don't have a calculator in front of us, I wouldn't expect us to go any further than that. All right, number 4, we're going to do the same problem, but we're just going to reverse the order. I'm not going to do the whole problem again. We're just going to rewrite the equation, the integral. So I have this little picture here of what this would look like. The bounds from 1 to 4 for y. So on the last problem there, the bounds for y are 1 to 4. and the bounds for x are root y to y. So this one right here is x equals root y, and this one right here is x equals y. Okay, x equals y is the same thing as y equals x. And if we square both sides of this first equation, we get x squared equals y. All right, so now if I want to rewrite the bounds here, what I'm going to need to do is I'm going to need to split this up a little bit in order to do this properly, okay? Because you can see up to, let me see if I can erase this here. There we go. Up to this part right here, the two equations that we're going to use are x squared and x. But once we get past that part anymore, we're no longer using x squared and x. We're still using x, but we're not using x squared anymore. We start using this line right here, which is just 4. So we're going to split this up into two integrals. Okay, the first one, the x bounds are 1 to 2. And the y bounds are y equals x to y equals x squared. Now I know they flip in there as well, but that should all take care of itself inside the integration. And then the second, the little green triangle that we have there, this is the second integral. If we do our double integral of x squared y cubed dy dx, the x bounds are 2 to 4, and the y bounds are from y equals x to y equals 4. So that would be how we switch the order of integration for that one. Clearly, that's not a better method of doing this. This would be a better method for doing this problem. But sometimes it's a little bit easier if we reverse the order. This one would be the opposite of that. This would be harder if we reverse the order. But we're just taking a look at how that would work in case we need to do that in the future. We're not going to go out solving that because we already know our answer anyway for number 3. To find the area of a region R, we calculate the double integral of the region of 1 dy dx, or dx dy, it doesn't matter what order you do that in. Okay, so we're going to do a little example with that. It says find the area of a triangle represented by x plus y is less than or equal to 1, if you want to know how to graph that. You can put that in slope-intercept form. So think of it as y equals negative x plus 1, okay? And then we're shading below that, but we're shading above x is equal to 0 and then to the right of y equals 0. So I have a picture there that you can see. Clearly, this is not the best method to find the area for this. You can just simply use the area of a triangle formula, but I'm just trying to show you how this works. So to set up your equation, your integral, I'm going to do this in two different ways. I'm going to do it in both. I'm going to reverse the order for both. So if, let's say we want to do dy dx first. Okay. The x bounds would go from 0 to 1. And the y bounds would go from 0 to whatever that diagonal line is. So that diagonal line, if we solve this for y, be y equals 1 minus x, or negative x plus 1. I'm just going to write it as 1 minus x. So the y bounds would be 0 to 1 minus x. Let's say we want to do it the other way. So we want to do our integral of 1 dx dy. Well, that's fine. It's not going to make it too much harder here. So now our y bounds would be 0 to 1. And our x bounds would be 0 to whatever that line is. So if we solve this equation for x this time, we would get 1 minus y. So it would be from 0 to 1 minus y. Okay? You can solve either of those to get our answer. We'll just solve the one on the left, but you can solve either. So if we integrate first with respect to y, we get y from 0 to 1 minus x dx. Substitute in 1 minus x minus 0 and now integrate that with respect to x. So we get x minus 1/2 x squared from 0 to 1. That gives us 1 minus 1/2 minus 0, which is 1/2, which we could have got a whole lot quicker by just simply doing the area of a triangle formula. But again, I just wanted to show you how that works. I want to take an easy look at one so you can see how the double integral of 1 will give you your area. So next thing is the average value of a function. So you have an average value formula in 2D that you learned last year. Now we're talking about an average value of a function f of x, y, so 3 dimensions. Okay, there's your formula for it. You take the double integral of the region of the function and divide it by the double integral of the region of 1. Okay, so here's an example. Find the average value of f of xy equals xy squared on the rectangle, and there's your region. All right, so our average is going to equal the double integral of the function. Now, you want to do dx or dy first, or dy dx first. It doesn't matter. I'm going to do dy dx. So my y bounds are 0 to 3, and my x bounds are 0 to 4. Over that same bounds 1 dy dx. All right, so the numerator is going to be a little bit harder to do than the bottom here. So to do the numerator, we're going to integrate first with respect to y, so that becomes 1/2 xy squared from 0 to 3 dx. The denominator you could probably figure out just by looking at that. It's a rectangle from 0 to 4 to 0 to 3. That's 4 times 3, so the denominator is just going to be 12. All right, so simplifying our numerator, substitute in 3 and then substitute in 0. Simplifying a little bit more, we get 9/2 x dx. Oh, I definitely made a mistake here. I copied on the problem wrong. Xy squared, I only copied on xy. That's all right. Simple fixes. Simple fixes. This would be 1/3 xy to the third. This would be 1/3. This would be 27. And then 27 over 3, this would just be 9. All right, back at it now. Let's go up here. So now we're integrating 9x from 0 to 4, so that'd be 9/2 x squared from 0 to 4 over 12. If we substitute 4 in there, we would get 16. So 16 over 2 is 8. 8 times 9 is 72. Put 0 in there to get 0 over 12. So our final answer here is 6. So the average value of that function f of xy over that rectangle is 6. Our next page is we're going to talk about a centroid. Okay, the centroid is the center of mass for a region with uniform density. Okay, so we use x star and y star to represent centroids. To get that, what we're going to do is we're going to double integrate x over the region over the double integral of 1. And that'll give you your x coordinate of the centroid, and do the same thing for the y coordinate, except replace x with y for the y coordinate of the centroid. Okay? I'm not going to go through any examples with that. It's pretty basic. Basically do the exact same thing we did for the last couple of problems, except we have the numerator as double integral of x or double integral of y. The big part of this chapter is the Gauss-Green formula. Okay? I like to use this notation for my Gauss-Green formula. Okay? Basically what we're trying to do is we're trying to make a double integral into a single integral that's actually doable for us, okay? So the integral from a to b, those would be your bounds, of m, which is some function, we'll get to that in a second, of xy times the derivative of x, plus n, which is another function of xy, times the derivative of y, all dt. The key here is that your parameterization must be counterclockwise, which is very easy to do. You just got to make sure that it's counterclockwise, okay? Since we want to use the Gauss-Green formula to measure a double integral of f, we must set m and n so that we would get this to be true, okay? So the key here is how to set that up. To do this, what we need to do is use the fundamental theorem of calculus. One convenient way to set this up is to let m equal 0 and n equal this integral here. Another way to do it is kind of switch that. Let n equal 0 and let m equal this integral here. Why do these both work? It goes off to what we've been doing earlier in this section. It's basically just switching the bounds, okay? It's doing like, instead of doing dx dy, it'd be doing dy dx, okay? So it's your choice. There's no wrong choice. I pretty much always use this one, so I can avoid the negative sign there, but it doesn't matter. Whatever you prefer, we should end up with the same answer in the end. So let's take a look at one of these. They take a long time to do, and we're actually not even going to be able to finish this problem because the integral itself is going to be too complicated for us to do by hand. But I can show you how this works by hand, and if we have easier ones to do by hand, you can then do them. But otherwise, we'll be doing most of these by using Mathematica. Use the Gauss-Green formula to find the volume of f of xy equals x squared y cubed above that ellipse. All right, the first thing we're going to want to do is parameterize the ellipse. So x of t is going to be 2 plus 3 cosine t. Y of t is going to be negative 1 plus 5 sine t. And we're going to use this parameterization because I know that's going to make it counterclockwise. If you put in 0 and then pi over 2 and pi, and you trace that ellipse out, it will be moving counterclockwise. All right, so now we're going to use this formula. Again, I'm going to use this one. You can use either one. So I'm going to set m of xy equal to 0. And I'm going to set n of xy equal to the integral from 0 to x of f of sy ds. Basically, I'm just copying down that formula right here. All right, so now let's simplify this. So the integral from 0 to x, f of sy, basically we're just putting s in for x into the f function. So that would be s squared y cubed ds. And if we integrate that, we get s cubed over 3 y cubed from 0 to x, which is x cubed over 3 y cubed minus 0. So finally, we can say n of xy is x cubed y cubed over 3. All right, so now we can use the Gauss-Green formula, which is this integral right here. All right, I'm just going to first copy that down so we can see where everything goes in our function. So volume equals the integral from a to b of m of x of t, y of t times x prime of t plus n of x of t, y of t times y prime of t dt. All right, so a to b are bounds. That's why we created the counterclockwise parameterization. That's from 0 to 2 pi. we let m of xy be 0. So that whole first part is all 0. So it all comes down to the second part here. N of x of t, y of t. So remember that n of xy, which is right here, but now we're going to say x is x of t. So x of t cubed, y of t cubed over 3 times y prime of t dt. So now we have the integral from 0 to 2 pi. X of t, remember x of t up here, is 2 plus 3 cosine t. Y of t is negative 1 plus 5 sine t. All over 3. And then y prime of t, that shouldn't be hard for us to do. Take the derivative of this. Derivative of negative 1 is 0. Derivative of 5 sine t is simply five cosine t dt. Okay? I'm not going to ask us to go any further than that. For something as complicated as this integral, we would use Mathematica to do this. Sometimes they work out really nicely, that they're easy to do, but in this case, this would be a very complex integral to try to do by hand. So we'll just leave that up to the machine, and we'll stop there. Okay? That'll do it for our Lesson 5 lecture. Feel free to email me with questions. Otherwise, good luck on the triads.